Rogue planets. The galaxy's wandering nomads. Somewhere in the vast spaces between stars, worlds drift alone through the cosmic night. These are the rogue planets. Massive spheres of rock and ice that wander through our galaxy without the warmth of a nearby sun, without the gentle pull of stellar gravity to guide their paths. They move through interstellar space like silent ships on an endless ocean, carrying with them stories of violent beginnings and mysterious possibilities. Tonight, as Earth turns peacefully beneath its blanket of atmosphere, countless rogue planets continue their solitary journeys through the Milky Way. Some are larger than Jupiter, their powerful magnetic fields creating invisible shields against cosmic radiation. Others are smaller, perhaps the size of Earth or Mars, their surfaces frozen solid, yet possibly harboring hidden oceans beneath miles of ice. These wandering worlds represent one of the universe's most intriguing mysteries, planets that exist in permanent night, yet may still pulse with the subtle rhythms of geological life. The story of rogue planets begins with understanding just how common they might be. Astronomers now estimate that our galaxy contains trillions of these cosmic nomads, potentially outnumbering the planets that orbit stars by a significant margin. This means that for every familiar world like Earth, Venus, or Mars, there may be dozens of rogue planets drifting unseen through the darkness, their presence detectable only through the most sophisticated astronomical techniques. These lonely worlds challenge everything we once thought we knew about planetary formation and the conditions necessary for life. They exist in a realm of perpetual twilight, where the only sources of heat come from within, the slow decay of radioactive elements deep in their cores, or the gradual cooling of primordial warmth left over from their formation billions of years ago. Yet even in this seemingly hostile environment, some rogue planets may harbor conditions suitable for life, hidden beneath their frozen surfaces in subsurface oceans that could rival those found on Jupiter's moon Europa. As we prepare to explore these mysterious worlds together, let the image of their silent journey bring a sense of calm. Picture the gentle motion of a planet moving through space at thousands of miles per hour, yet appearing motionless against the backdrop of distant stars. There is something profoundly peaceful about these solitary travelers, worlds that have found their own path through the cosmos, independent of the gravitational bonds that tie most planets to their parent stars. The birth of cosmic nomads. The formation of rogue planets tells a story of cosmic violence and celestial mechanics that begins in the chaotic early days of planetary systems. Most planets form within the swirling disk of gas and dust that surrounds young stars, gradually accumulating material until they reach planetary size. But not all of these forming worlds remain in their birthplaces. Some become cosmic exiles through processes that reshape entire solar systems. The most common path to becoming a rogue planet involves gravitational ejection, a celestial game of billiards played on a massive scale. When young planetary systems contain multiple large planets, their gravitational interactions can become unstable over millions of years. Picture two Jupiter-sized worlds slowly spiraling toward each other in their orbits around a young star. As they approach, their immense gravitational fields begin to distort each other's paths, creating increasingly elliptical orbits that swing the planets closer to and farther from their star with each pass. During these close encounters, one planet typically emerges as the gravitational winner, settling into a stable orbit, while the other gets flung outward with tremendous force. The ejected planet carries so much momentum that it completely escapes its star's gravitational pull, launching into interstellar space at speeds of dozens of miles per second. This process is surprisingly common in young planetary systems, where the gravitational architecture hasn't yet settled into the stable configuration we see in our own solar system today. Computer simulations suggest that most planetary systems go through periods of such instability, particularly during their first 100 million years. The early solar system likely experienced similar chaos, with planets migrating inward and outward as they gravitationally influenced each other's orbits. Some models suggest that our solar system may have once contained additional planets that were ejected during this turbulent period, now wandering somewhere in the depths of interstellar space. But gravitational ejection isn't the only way rogue planets come to exist. Some of these worlds may have formed in isolation, never bound to any star at all. In the dense stellar nurseries where new stars are born, the same gravitational processes that create stars can sometimes produce planetary mass objects that form independently. These are called free-floating planets, or isolated planetary mass objects, and they represent a fascinating category of cosmic bodies that blur the line between planets and brown dwarfs. The formation process for isolated rogue planets begins in regions where interstellar gas and dust are particularly dense. Instead of being incorporated into the disk around a forming star, small pockets of material can collapse under their own gravity to form planet-sized objects. These worlds never experience the warmth of stellar radiation during their formation, beginning their existence already in the deep cold of interstellar space. Recent observations have revealed that rogue planet formation may be more common than previously thought. The Orion Nebula, one of the nearest star-forming regions to Earth, contains numerous isolated planetary mass objects that appear to have formed independently rather than being ejected from existing systems. These discoveries suggest that the process of planetary formation is far more diverse and complex than astronomers once believed. The size range of rogue planets spans from objects smaller than Mercury to super-Jupiters with masses many times that of our solar system's largest planet. The smaller rocky rogue planets likely formed in the inner regions of planetary systems before being ejected, while the larger gas giants either formed farther from their stars or accumulated their massive atmospheres during independent formation in interstellar space. Understanding the origins of rogue planets also reveals important details about planetary system evolution. The presence of rogue planets in our galaxy serves as evidence for widespread dynamical instability in young planetary systems. Each wandering world represents a system that underwent significant reorganization, possibly affecting the orbits of remaining planets and influencing their potential for habitability. Some rogue planets may have been ejected along with their moons, creating miniature systems that travel together through interstellar space. These rogue planet-moon systems could potentially maintain tidal heating between the planet and its satellite, providing an additional source of internal energy that might support subsurface oceans or geological activity even in the absence of stellar heating. Now, close your eyes and picture how all of this might look. Imagine a young star system 4 billion years ago, with several massive planets slowly orbiting through clouds of remaining dust and debris. Watch as their paths gradually shift over millions of years, bringing them closer together until their gravitational dance becomes unstable. See one world accelerating outward, past the orbits of smaller planets, beyond the edge of the stellar system, and into the vast darkness between stars, where it will wander alone for billions of years to come. The hidden multitudes. The true scale of rogue planet populations in our galaxy defies easy comprehension. Current estimates suggest that the Milky Way contains between 1 and 10 trillion rogue planets, a number so vast that it challenges our understanding of planetary formation and the structure of our galaxy itself. To put this in perspective, Our galaxy contains roughly 400 billion stars, meaning that rogue planets may outnumber stars by a factor of 10 or more. These estimates come from a combination of direct observations, gravitational microlensing surveys, and theoretical models of planetary system evolution. Gravitational microlensing, the primary method for detecting rogue planets, occurs when one of these wandering worlds passes directly between Earth and a more distant star. The rogue planet's gravity acts like a lens, briefly magnifying the light from the background star in a characteristic pattern that reveals the presence of the intervening world. The duration and shape of these microlensing events provide information about the mass of the rogue planet and its distance from Earth. Events lasting a few hours typically indicate Earth-mass rogue planets, while events lasting days or weeks suggest more massive worlds comparable to Jupiter or Saturn. The frequency of these events allows astronomers to estimate the overall population of rogue planets in different mass ranges. Several major surveys have been dedicated to finding rogue planets through microlensing, including the Optical Gravitational Lensing Experiment, OGLM, and the Microlensing Observations in Astrophysics, MOA, project. These surveys monitor millions of stars simultaneously, looking for the brief, brightening events that betray the presence of a rogue planet crossing the line of sight. Over the past 2 decades, these projects have detected dozens of rogue planet candidates and provided the statistical foundation for estimating the total population. The distribution of rogue planets throughout the galaxy appears to follow the overall distribution of stellar populations, with higher concentrations toward the galactic center and lower densities in the outer regions where our solar system resides. This pattern makes sense given that most rogue planets likely originated in stellar systems before being ejected, so their current locations should roughly trace the birthplaces of stars throughout the galaxy's history. But the numbers alone don't capture the full significance of rogue planets in our cosmic neighborhood. Within a sphere extending just 50 light-years from our solar system, a region that contains roughly 1,500 stars, there may be 10,000 or more rogue planets wandering through the interstellar medium. The nearest rogue planet to Earth could be closer than the nearest star beyond our Sun, Proxima Centauri. Yet it would remain completely invisible to even our most powerful telescopes. The mass distribution of rogue planets shows interesting patterns that provide clues about their formation mechanisms. Surveys suggest that lower-mass rogue planets, comparable to Earth or smaller, are more common than massive gas giants. This distribution matches theoretical predictions for gravitational ejection, since smaller planets are more easily perturbed from their orbits during dynamical interactions with larger worlds. However, the census of rogue planets remains incomplete, particularly for the most massive examples. Super-Jupiter rogue planets with masses approaching the boundary between planets and brown dwarf stars are difficult to distinguish from isolated low-mass stars using current detection methods. These massive wanderers may be more common than current surveys suggest, representing a hidden population of objects that formed through stellar rather than planetary processes. The temporal aspects of rogue planet populations add another layer of complexity to understanding their numbers. Computer simulations suggest that the rate of rogue planet ejection was highest during the early epochs of galactic evolution, when stellar formation rates were much higher and planetary systems underwent more frequent dynamical instability. This means that many of the rogue planets wandering through our galaxy today may be ancient worlds that were ejected billions of years ago, when the Milky Way was a much more active and chaotic place. Some rogue planets may have been wandering for so long that they've traveled completely across the galaxy multiple times. A rogue planet ejected from a star system near the galactic center 8 billion years ago could have reached the outer spiral arms by now, assuming typical velocities of tens of miles per second. These ancient nomads carry with them chemical signatures from their birthplaces that may be very different from the composition of stars and planets forming today. The existence of rogue planet clusters adds another dimension to their population structure. Rather than being uniformly distributed through interstellar space, some rogue planets appear to travel in loose associations that may represent the remnants of disrupted stellar systems or the products of particularly violent ejection events. These clusters could contain dozens of rogue planets moving through space together, creating temporary neighborhoods in the otherwise empty regions between stars. Future surveys will dramatically improve our knowledge of rogue planet populations. NASA's upcoming Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct the most comprehensive search for rogue planets ever attempted. Its wide-field infrared camera and precise photometry capabilities will enable the detection of much smaller and more distant rogue planets than current ground-based surveys can find. The Roman Telescope's survey is expected to discover thousands of new rogue planets and provide the first accurate census of these objects across a wide range of masses. This information will help astronomers understand whether current population estimates are correct or if the galaxy contains even more rogue planets than previously thought. If this peaceful view of the cosmos brings you calm, consider returning here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars. The chemistry of eternal night in the perpetual darkness of rogue planets. Chemical processes unfold according to principles that operate at the absolute limits of molecular behavior, where temperatures approach the theoretical minimum and reaction rates slow to timescales measured in geological epochs. These extreme chemical environments create opportunities for the formation and preservation of complex molecular structures that would be quickly destroyed in the high-energy environments of planets bathed in stellar radiation. The surface chemistry of rogue planets proceeds through mechanisms dominated by cosmic ray bombardment and the slow sublimation and recondensation of volatile compounds, as internal heat sources create subtle temperature variations across planetary surfaces. Cosmic rays provide the primary source of chemical energy in these cold environments, breaking molecular bonds and creating reactive species that can participate in synthesis reactions, despite the extremely low temperatures that would normally inhibit chemical activity. Water ice on rogue planet surfaces exists in crystalline forms that can incorporate other molecular species into their lattice structures, creating complex ice formations that serve as natural laboratories for low-temperature chemistry. These ice crystals can preserve organic compounds and reactive species for billions of years, while facilitating slow chemical reactions between trapped molecules through quantum tunneling effects that allow reaction barriers to be overcome even at near absolute zero temperatures. The formation of complex organic molecules on rogue planets follows pathways that begin with simple precursors like carbon monoxide, methane, and ammonia that condense from trace atmospheres or are delivered by interstellar dust grains and cometary impacts. Under the influence of cosmic ray radiation, these simple molecules undergo slow polymerization reactions that can build increasingly complex organic structures over millions of years of exposure. Laboratory experiments simulating rogue planet surface conditions have demonstrated that amino acids, nucleotide bases, and other biologically important molecules can form through cosmic ray-induced chemistry in ice matrices at temperatures characteristic of interstellar space. These experimental results suggest that the surfaces of rogue planets may accumulate significant inventories of prebiotic organic compounds over their billions of years of wandering through the galaxy. The subsurface chemistry of rogue planets involves hydrothermal processes occurring in buried oceans where liquid water interacts with rocky materials under high pressure and moderate temperatures maintained by radioactive heating. These environments support extensive water-rock interactions that can create complex mineral assemblages and dissolved chemical species that rival the diversity found in Earth's deep ocean hydrothermal systems. Hydrothermal circulation in rogue planet oceans transports dissolved materials between different chemical environments, creating opportunities for the concentration and purification of specific compounds through processes such as fractional crystallization and selective adsorption onto mineral surfaces. These natural chemical separation processes can create localized environments where particular types of chemistry are favored over geological timescales. The absence of photochemical processes on rogue planets eliminates many of the destructive chemical pathways that limit the accumulation of complex organic molecules on planets exposed to stellar ultraviolet radiation. Without photodissociation and photooxidation reactions, organic compounds can persist and accumulate on rogue planet surfaces and in subsurface environments for periods extending far beyond what would be possible on planets orbiting active stars. Radiolysis, the breakdown of molecules by ionizing radiation, represents the primary destructive chemical process affecting organic compounds on rogue planets. But the low flux of cosmic rays compared to stellar radiation means that radiolytic destruction proceeds much more slowly than photochemical destruction. This allows complex molecules to achieve higher steady-state concentrations than would be possible in stellar radiation environments. The chemical evolution of rogue planet atmospheres involves gradual changes in composition, as radioactive decay in planetary interiors releases noble gases and other volatile species that slowly accumulate in tenuous atmospheric envelopes. These evolved atmospheres can develop unique chemical compositions that reflect billions of years of outgassing and atmospheric processing in the absence of stellar influences. Catalytic processes involving mineral surfaces play crucial roles in rogue planet chemistry by providing reaction sites where molecular concentrations can be enhanced and reaction barriers can be lowered through surface interactions. Clay minerals, metal oxides, and other catalytically active surfaces can facilitate the formation of complex organic molecules, even under the extreme conditions found on rogue planet surfaces. The preservation of chemical information on rogue planets extends far beyond what is possible on geologically active worlds, with molecular structures and isotopic signatures remaining unchanged for billions of years in the stable cold storage provided by near absolute zero surface temperatures. This chemical stability creates natural archives that preserve records of chemical processes that occurred during planetary formation and early evolution. Sublimation and recondensation cycles driven by seasonal temperature variations created by changes in internal heat output can concentrate chemical species in specific locations on rogue planet surfaces, creating chemical gradients and specialized microenvironments where particular types of reactions are favored. These processes can lead to the formation of chemical deposits, with compositions very different from the bulk surface materials. The interaction between magnetic fields and charged chemical species in rogue planet atmospheres creates unique electrochemical environments where electric fields can drive chemical reactions that would not occur under purely thermal conditions. These plasma chemical processes can synthesize complex molecules through pathways that are completely absent from the chemistry of neutral gas phase reactions. Isotopic fractionation processes on rogue planets proceed through mechanisms that can create distinctive isotopic signatures in chemical compounds, providing potential tools for identifying materials that originated on rogue planets versus other types of astronomical objects. These isotopic fingerprints could serve as biomarkers for rogue planet chemistry if samples from these worlds are ever returned to Earth for analysis. The study of rogue planet chemistry provides insights into the fundamental limits of chemical complexity under extreme conditions, revealing how molecular systems can evolve and persist in environments that represent the coldest and most isolated chemical laboratories in the galaxy. Understanding these extreme chemical processes helps define the boundary conditions for chemistry throughout the universe. Chemical gradients created by the flow of heat from rogue planet interiors toward their surfaces establish zones with different chemical environments that can support different types of molecular synthesis and transformation reactions. These thermal gradients create natural chemical reactors where temperature-dependent reactions can proceed at optimal rates in specific depth ranges within planetary crusts. The potential for autocatalytic chemical networks on rogue planets involves self-sustaining reaction systems where the products of chemical reactions catalyze further reactions, creating feedback loops that can maintain complex chemistry over geological timescales. These autocatalytic systems represent possible pathways toward the emergence of protobiological chemical organization in extreme environments. Now, close your eyes and picture how all of this might look. Imagine the slow, patient chemistry unfolding on a rogue planet's surface over millions of years, with cosmic rays gently breaking and reforming molecular bonds in ice crystals that stretch across continents, while far below, in hidden seas warmed by radioactive decay, complex chemical gardens bloom in eternal darkness, building the molecular foundations that could someday support the emergence of life itself. Rogue worlds as cosmic time capsules. Each rogue planet wandering through the galaxy serves as a pristine time capsule, preserving within its structure and composition a detailed record of the conditions that existed during its formation billions of years ago. Unlike planets that remain bound to their parent stars and continue to evolve under stellar influences, rogue planets effectively freeze their development at the moment of ejection, maintaining their original characteristics virtually unchanged throughout their subsequent journey through interstellar space. The isotopic compositions of rogue planets provide direct windows into the nucleosynthetic processes that enrich their birth environments with heavy elements produced by previous generations of stars. Each chemical element carries isotopic ratios that reflect the specific stellar sources that contributed material to the protoplanetary disk where the rogue planet formed, creating a chemical fingerprint that identifies not only when the planet formed, but also the stellar population characteristics of its birth region. Oxygen isotope ratios in rogue planet materials reveal information about the temperature and chemical conditions in the protoplanetary nebula during the condensation of rocky materials, while silicon and magnesium isotopes provide insights into the types of supernovae and stellar nucleosynthesis processes that enriched the local interstellar medium with heavy elements before planetary formation began. These isotopic signatures remain unchanged for billions of years, preserving a fossil record of galactic chemical evolution. The mineral assemblages found in rogue planet interiors reflect the pressure and temperature conditions that existed during planetary accretion and early differentiation processes. High-pressure minerals formed during planetary core formation preserve information about the gravitational energy release and heating that occurred as planetesimals collided and merged to build planetary mass objects in the early solar system environment. Crystalline structures in rogue planet materials can preserve evidence of magnetic field orientations and strengths that existed during planetary formation, recorded in the alignment of magnetic minerals that formed during the cooling and solidification of planetary interiors. These paleomagnetic records provide information about the early evolution of planetary dynamos and the magnetic environment of the nascent planetary system. The volatile inventories of rogue planets preserve samples of the gas and ice compositions that characterized their birth environments, including water ice, carbon dioxide, methane, ammonia, and other compounds that condensed from the cooling protoplanetary nebula. The isotopic compositions of these volatiles provide information about the sources of water and organic materials in early planetary systems and the processes that delivered these life-essential compounds to forming planets. Atmospheric compositions of gas giant rogue planets represent fossilized samples of the nebular gas from which they accreted their massive gaseous envelopes during planetary formation. The noble gas abundances and isotopic ratios in these atmospheres provide direct measurements of the composition of the solar nebula and enable comparisons with other stellar systems to understand how nebular compositions vary with stellar mass, metallicity, and formation environment. The surface geology of rocky rogue planets preserves evidence of early bombardment periods when planetary surfaces were reshaped by impacts from asteroids and comets left over from planetary formation. Impact crater distributions, ejected deposits, and shock metamorphic minerals in rogue planet crustal materials provide information about the intensity and duration of early bombardment phases that affected all planetary systems during their first billion years of evolution. Organic compounds preserved in rogue planet materials may include pristine samples of the prebiotic chemistry that characterized early planetary environments before the development of life. These organic inventories could contain amino acids, nucleotide bases, lipid precursors, and other biochemically important molecules that were synthesized during planetary formation through processes involving cosmic ray irradiation, shock heating, and hydrothermal activity. The internal structure of rogue planets reflects the accretion and differentiation processes that operated during their formation, with core mantle crust layering that preserves information about the timing and efficiency of metal-silicate separation, the heat sources that drove early planetary melting, and the chemical processes that concentrated different elements in different planetary reservoirs. Primordial heat signatures in rogue planet interiors provide information about the gravitational energy release and radioactive heating that characterized planetary formation processes. The current thermal state of a rogue planet's interior reflects the balance between heat generation during accretion and heat loss over billions of years of cooling, creating a thermal fossil record of early planetary energetics. The satellite systems of rogue planets that retained their moons during ejection preserve information about the late stages of planetary formation, when satellite capture and orbital evolution processes shaped the architecture of planetary systems. Moon compositions, orbital characteristics, and tidal evolution histories recorded in satellite systems provide insights into the dynamical environment of early planetary systems. Chemical zoning patterns in rogue planet interiors preserve records of the sequence of accretion events that built these worlds from smaller planetesimals, with different compositional layers reflecting the changing chemistry of the protoplanetary disk as planetary formation progressed. These compositional gradients provide insights into the timescales and mechanisms of planetary growth in early stellar systems. The absence of ongoing geological activity on many rogue planets means that their surfaces and shallow interiors remain largely unmodified since the time of ejection, preserving impact craters, volcanic features, and tectonic structures that record the final phases of active planetary evolution before departure from their parent stellar systems. These geological features provide snapshots of planetary surface processes that operated billions of years ago. Cosmic ray exposure records in rogue planet surface materials provide information about their transit times through interstellar space and the galactic environments they have encountered during their wandering journey. Cosmogenic isotope production rates in surface rocks can be used to calculate how long rogue planets have been exposed to cosmic ray bombardment providing minimum ages for their ejection from stellar systems. The study of rogue planets as time capsules requires the development of new analytical techniques capable of extracting maximum information from potentially tiny samples that might be returned by future exploration missions. Advanced mass spectrometry, crystallographic analysis, and microscopic imaging techniques will be needed to decode the complex records preserved in rogue planet materials. Comparative studies of rogue planets with different formation ages provide opportunities to trace the evolution of planetary formation processes and galactic chemical enrichment over cosmic time. Older rogue planets formed when the galaxy had lower metallicity and different stellar populations than exist today, potentially showing systematic differences in their compositions that reflect the changing galactic environment over billions of years. The preservation potential of biological materials in rogue planet environments remains an open question that could have profound implications for astrobiology if life ever existed on these worlds before their ejection from stellar systems. The extreme cold and stable chemical conditions on rogue planet surfaces could potentially preserve biosignatures for billions of years, creating natural museums of ancient life that could survive far longer than biological materials on geologically active worlds. The interstellar journey. The passage of rogue planets through interstellar space represents one of the longest and most solitary journeys possible in the physical universe. With these cosmic wanderers traversing distances measured in hundreds of thousands of light-years over timescales that span significant fractions of the galaxy's entire evolutionary history. During these epic voyages, rogue planets encounter a diverse array of interstellar environments that gradually modify their surfaces, atmospheres, and even internal structures through subtle but persistent physical and chemical processes. The interstellar medium through which rogue planets travel varies dramatically in density, temperature, and composition, depending on the galactic location and local astronomical environment. Rogue planets crossing through molecular clouds encounter regions where hydrogen densities can reach thousands of atoms per cubic centimeter, creating drag forces that slowly decelerate planetary motion and can cause measurable changes in orbital trajectories over millions of years of passage through these dense regions. Dust grain impacts represent a constant source of surface modification for rogue planets during their interstellar journey, with microscopic particles striking planetary surfaces at relative velocities of tens of miles per second and gradually eroding exposed materials through a process analogous to cosmic sandblasting. Over billions of years, this dust bombardment can remove significant amounts of surface material while simultaneously depositing new materials with chemical compositions reflecting the local interstellar environment. The gravitational interactions between rogue planets and massive objects encountered during their galactic journey can deflect planetary trajectories and occasionally capture rogue planets into new stellar systems, effectively ending their period of interstellar wandering. Close encounters with stars, brown dwarfs, stellar remnants, or other rogue planets can alter velocities and directions while providing opportunities for temporary gravitational capture that might create new planetary systems. Magnetic field interactions between rogue planets and the galactic magnetic field create complex plasma physics phenomena that can affect planetary magnetospheres and potentially influence atmospheric retention and surface chemistry. The galactic magnetic field, though extremely weak by terrestrial standards, can interact with planetary magnetic fields over the vast timescales of interstellar transit to create cumulative effects that modify planetary magnetic environments. Cosmic ray bombardment during interstellar transit provides a continuous source of high-energy particle radiation that penetrates deep into planetary surfaces and atmospheres, driving chemical reactions and creating radioactive isotopes that serve as chronometers for measuring transit times through different galactic environments. The cosmic ray flux varies significantly depending on galactic location, with higher intensities near the galactic center and lower intensities in the outer spiral arms. The thermal evolution of rogue planets during interstellar transit involves a gradual cooling process that continues for billions of years as internal heat sources slowly decay and heat is lost to the cosmic background radiation. This cooling process affects atmospheric retention, geological activity, and the potential for maintaining subsurface liquid water, creating evolutionary timelines that can extend for periods longer than the current age of the universe. Encounters with interstellar objects such as comets, asteroids, and brown dwarfs provide opportunities for material exchange and impact events that can temporarily alter rogue planet surface conditions and atmospheric compositions. Large impact events can create temporary atmospheres through the vaporization of surface materials, while smaller impacts contribute to gradual surface evolution through impact gardening and material mixing processes. The rotation rates of rogue planets can change during interstellar transit through tidal interactions with massive objects encountered during close passages, with these rotational changes affecting internal heat generation through tidal dissipation and potentially influencing magnetic field generation in planetary cores. Changes in rotation rate can also affect atmospheric circulation patterns and surface temperature distributions. Stellar encounter rates for rogue planets depend on their galactic orbits and the local stellar density in their current galactic environment. With planets traveling through the dense central regions of the galaxy experiencing more frequent stellar encounters than those wandering through the sparse outer regions. These encounter statistics help determine the probability of rogue planet capture and the likelihood of experiencing disruptive gravitational interactions. The accumulation of interstellar material on rogue planet surfaces creates opportunities for studying the composition and evolution of the interstellar medium through analysis of deposited materials that record the chemical and isotopic signatures of different galactic environments encountered during planetary wandering. These surface deposits provide natural samples of interstellar materials that would be difficult to study through any other means. Atmospheric evolution during interstellar transit involves complex interactions between atmospheric escape processes, cosmic ray-induced chemistry, and the occasional replenishment of atmospheric constituents through outgassing from planetary interiors or impacts from interstellar objects. The balance between these competing processes determines whether rogue planets can maintain atmospheric envelopes over cosmic timescales. Navigation through the galaxy's gravitational potential well affects rogue planet trajectories in ways that depend on planetary mass, velocity, and the distribution of gravitational sources encountered during galactic orbit. Massive rogue planets with high velocities can maintain relatively straight-line trajectories through interstellar space, while smaller, slower-moving planets are more susceptible to gravitational deflection by stellar encounters. The chemical weathering of rogue planet surfaces during interstellar transit proceeds through mechanisms involving cosmic ray sputtering, micrometeorite bombardment, and sublimation of volatile compounds driven by cosmic ray heating. These weathering processes create regolith layers with distinctive chemical and physical properties that reflect billions of years of exposure to the interstellar environment. Radiation exposure during interstellar transit creates distinctive patterns of cosmogenic isotope production in rogue planet surface materials that can be used to reconstruct transit histories and determine the galactic environments through which individual planets have traveled. These isotopic records provide unique insights into galactic structure and the distribution of cosmic ray sources throughout the Milky Way. The possibility of encountering other rogue planets during interstellar transit raises intriguing questions about the formation of rogue planet binary systems and the potential for gravitational capture events that could create temporary or permanent associations between previously independent wandering worlds. Such encounters would be extremely rare, but could produce observable signatures in the orbital characteristics of captured planets. Climate evolution on rogue planets during interstellar transit involves gradual changes in atmospheric composition, surface temperature distributions, and internal heat flow patterns that occur over timescales of hundreds of millions to billions of years. Understanding these long-term climate changes helps predict the current conditions on rogue planets that have been wandering through interstellar space for significant fractions of galactic history. The interstellar journey of rogue planets provides unique opportunities for studying fundamental physical processes under extreme conditions that cannot be replicated in laboratory environments or observed in the dynamic conditions around stars. These natural experiments in planetary physics help test theoretical models of planetary evolution and provide insights into the behavior of matter under conditions that represent the ultimate limits of planetary environments. Final reflections. The silent majority. As we draw our cosmic journey to its gentle conclusion, the profound implications of rogue planets continue to resonate through our understanding of the universe, revealing that the galaxy may be dominated not by the familiar worlds that orbit stars, but by these silent wanderers that have found their own paths through the cosmic dark. Their existence fundamentally alters our perspective on planetary abundance, habitability, and the distribution of complex matter throughout the Milky Way. The sheer scale of rogue planet populations transforms our conception of what constitutes normal planetary existence in the galaxy. If current estimates prove accurate, the vast majority of planetary matter exists in the form of worlds that have never known the warmth of stellar radiation, that have never experienced the cycle of day and night, and that pursue their evolution according to principles governed entirely by internal processes and the gentle influences of interstellar space. These cosmic nomads challenge traditional definitions of planetary systems and force us to expand our understanding of habitability far beyond the narrow band of distances around stars where liquid water can exist on planetary surfaces. The possibility that rogue planets may harbor vast subsurface oceans heated by radioactive decay suggests that the galaxy may contain countless hidden biospheres, each evolving independently in the perpetual darkness between stars. The temporal scales involved in rogue planet evolution dwarf the lifespans of most stellar phenomena, with these worlds potentially maintaining stable internal conditions for periods that extend far beyond the era when star formation will cease in our galaxy. This remarkable longevity means that rogue planets could serve as the final refugees for complex chemistry, and possibly even life long after the last stars have exhausted their nuclear fuel and the galaxy has entered its final phase of cosmic evolution. The discovery that planetary formation is apparently so prolific that stellar systems regularly eject significant fractions of their planetary populations reveals the universe to be far more dynamic and violent than previous generations of astronomers imagined. The billions of years that seem to represent stable evolutionary timescales from human perspective may actually be filled with dramatic reorganization events that reshape planetary system architecture and scatter worlds across interstellar space. The preservation of primordial conditions on rogue planets creates natural laboratories that maintain pristine samples of the materials and processes that characterized planetary formation throughout galactic history. These worlds serve as cosmic museums where the chemical signatures and physical structures created during planetary birth remain unchanged for billions of years, providing unprecedented opportunities to study planetary formation processes across the full range of galactic environments and evolutionary epochs. The potential for life on rogue planets, sustained by internal heat sources and sheltered beneath protective layers of ice and rock, suggests that biological evolution may be far more resilient and adaptable than previously thought. Life forms that could emerge and thrive in the perpetual darkness of rogue planet subsurface oceans would represent completely independent experiments in biological organization, potentially developing along pathways that have no parallel among organisms that evolved under stellar radiation. The technological challenges involved in detecting and exploring rogue planets will drive advances in observational astronomy, spacecraft propulsion, and robotic exploration that benefit many other areas of space science and human space exploration. The extreme requirements of rogue planet missions represent ultimate tests of our technological capabilities, while providing motivation for developing the tools needed for true interstellar exploration. The philosophical implications of widespread rogue planet populations touch on fundamental questions about the prevalence of complex environments in the universe and the potential for intelligence and consciousness to emerge in isolation from stellar energy sources. These considerations expand our perspective on the possible forms that advanced civilizations might take and the environments where technological development could occur. The gravitational interactions and orbital dynamics that create rogue planets through ejection processes reveal the universe to be far more interconnected than it might appear, with events in one stellar system potentially affecting the distribution of planetary materials across vast regions of the galaxy. Understanding these connections helps reveal the hidden relationships that link seemingly isolated astronomical objects across enormous distances and timescales. The magnetic fields, atmospheric processes, and geological activity that characterize rogue planets demonstrate that complex physical and chemical processes can operate independently of stellar influences, powered instead by the internal energy sources that all massive objects possess through radioactive decay and gravitational energy. This independence suggests that planetary complexity may be far more widespread than estimates based solely on stellar habitable zones would indicate. The future exploration of rogue planets promises to reveal entirely new categories of planetary environments and potentially revolutionary discoveries about the conditions that can support complex chemistry and biological processes. These missions will test our understanding of planetary science under the most extreme conditions, while potentially answering fundamental questions about the prevalence and diversity of life in the universe. The patient journey of rogue planets through interstellar space embodies a kind of cosmic persistence that transcends human timescales and provides perspective on the deep rhythms that govern galactic evolution. These worlds demonstrate that the universe contains structures and processes that operate on timescales so vast that they challenge our ability to comprehend their full implications for cosmic evolution and the ultimate fate of complex matter. As we settle into the quietude of sleep, let the image of these wandering worlds bring peace and perspective to our earthbound concerns. Somewhere in the darkness between stars, trillions of planets continue their ancient journeys through space, each one a complete world unto itself, carrying within its frozen surface and hidden depths all the materials and energy needed for its own quiet existence in the vast spaces of the galaxy. These silent travelers remind us that the universe is far more abundant and diverse than we can see from our small perspective on one planet orbiting one star among billions. They suggest that complexity, beauty, and perhaps even life itself may be far more common than we dare to imagine. Hidden in the dark spaces that dominate the galaxy's volume, but remain largely invisible to our current observational capabilities. In this gentle understanding of our place in a universe filled with wandering worlds, Find rest knowing that the cosmos contains far more wonders than we have yet discovered, far more stories than we will ever fully know, and far more possibilities for complexity and beauty than we can currently comprehend. The galaxy turns slowly around its distant center, carrying with it countless rogue planets that pursue their patient paths through the cosmic night. Each one a reminder that even in the apparent emptiness of space, worlds drift silently by, complete and self-contained, following their own quiet destinies through the endless darkness between the stars. Sleep now and dream of wandering worlds, drifting peacefully through the quiet darkness between stars, each one complete in itself, each one following its own path through the cosmic deep, where time moves slowly and distances are measured in the patient progress of worlds that have learned to find their way without the guidance of any sun, carrying within themselves all the mystery and wonder of planetary existence in its purest form, free from the bonds of stellar gravity, pursuing their own eternal dance through the vast spaces of our galaxy. Brings you calm. Consider returning here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars. NASA's hunt for the invisible. In the coming years, one of humanity's most sophisticated space observatories will turn its attention to finding the galaxy's hidden population of rogue planets. The Nancy Grace Roman Space Telescope, named after NASA's first chief of astronomy, represents the next generation of space-based planet hunting, designed specifically to detect the wandering worlds that remain invisible to most current survey methods. The Roman telescope's approach to finding rogue planets relies on an improved version of the gravitational micro-lensing technique that has already revealed dozens of these cosmic nomads. Unlike ground-based telescopes that must peer through Earth's turbulent atmosphere, Roman will observe from the stable environment of space, enabling it to detect much smaller and more subtle microlensing events than ever before possible. The telescope's wide-field infrared instrument will simultaneously monitor over 100 million stars toward the center of our galaxy, where the high density of background stars provides the best opportunities for microlensing detections. This survey will be thousands of times more sensitive than previous efforts, capable of detecting rogue planets as small as Mars, or even smaller rocky worlds that previous surveys couldn't identify. Roman's microlensing survey will unfold over several years, with the telescope repeatedly observing the same regions of sky to build up a comprehensive database of microlensing events. Each observation will capture precise measurements of stellar brightness across multiple infrared wavelengths, allowing astronomers to distinguish genuine rogue planet detections from other astronomical phenomena that can mimic microlensing signatures. The technical specifications of Roman's capabilities reveal the extraordinary precision required for this cosmic detective work. The telescope will measure stellar brightnesses to better than 1 part in 10,000, enabling it to detect the brief, subtle brightenings caused by Earth mass or smaller rogue planets passing in front of distant stars. These events may last only a few hours and increase the background star's apparent brightness by less than 1%, requiring exceptional instrumental stability and data processing techniques. Beyond simply counting rogue planets, Roman's survey will provide unprecedented information about their characteristics and distribution throughout the galaxy. By measuring the duration, amplitude, and detailed shape of microlensing light curves, astronomers will be able to determine not only the masses of individual rogue planets, but also their distances from Earth and their velocities through interstellar space. The telescope's infrared capabilities offer particular advantages for studying rogue planets. While these worlds emit virtually no visible light, they do radiate heat in the infrared spectrum from their slowly cooling interiors. Roman may be able to directly detect the thermal emission from the largest rogue planets, providing complementary information to supplement the microlensing discoveries and offering insights into their atmospheric properties and internal structure. Roman's survey design will also enable the detection of rogue planet systems, cases where ejected planets retain their moons during the ejection process. These binary microlensing events produce more complex light curves that reveal the presence of multiple objects, potentially uncovering intact planet-moon systems wandering through interstellar space. Such discoveries would provide valuable information about the ejection process and the conditions under which planetary satellites can survive the violent transition from bound to free-floating status. The statistical power of Roman's rogue planet survey extends far beyond individual discoveries. By detecting thousands of these objects across a wide range of masses and distances, the mission will provide the first comprehensive census of free-floating planets in our galaxy. This information will help resolve current uncertainties about rogue planet populations and provide crucial data for testing theories of planetary formation and system evolution. Roman's observations will also address fundamental questions about the relationship between rogue planets and their parent stellar populations. By correlating rogue planet detections with the properties of nearby stars and stellar clusters, astronomers will gain insights into which types of stellar systems are most likely to eject planets and under what circumstances these ejection events occur. The mission timeline for Roman's rogue planet survey reflects the long-term nature of microlensing observations. The telescope will spend approximately 2 years conducting intensive monitoring of the galactic bulge region, accumulating the observational baseline necessary to detect and characterize rogue planets across a wide range of orbital periods and masses. Additional time will be devoted to follow-up observations of the most interesting discoveries, potentially including attempts to directly image the most massive rogue planets at infrared wavelengths. Advanced data processing techniques will be essential for extracting rogue planet signals from Roman's observations. The telescope will generate enormous amounts of data, requiring sophisticated algorithms to identify genuine microlensing events among the millions of variable stars and instrumental effects that can mimic planetary signatures. Machine learning approaches are being developed to help automate this process and ensure that subtle rogue planet detections aren't overlooked in the vast dataset. The international collaboration aspect of Roman's rogue planet survey brings together astronomers from around the world who specialize in microlensing observations and planetary system dynamics. Ground-based telescopes will provide crucial follow-up observations of Roman's discoveries, helping to confirm planetary interpretations and refine mass estimates through additional photometric and spectroscopic measurements. Expected discoveries from Roman's survey include not only large numbers of individual rogue planets, but also the first statistical constraints on how rogue planet properties vary with galactic environment. The mission may discover that rogue planets are more common in certain regions of the galaxy, or that their mass distribution varies depending on the local stellar population characteristics. The broader implications of Roman's rogue planet discoveries will extend to many areas of astronomy and planetary science. Understanding the true abundance and properties of free-floating planets will inform models of planetary formation, help constrain theories of early solar system evolution, and provide new perspectives on the prevalence of potentially habitable environments in the galaxy. Frozen worlds with warm hearts. Despite their exile from stellar warmth, many rogue planets may harbor environments capable of supporting life, hidden beneath their frozen surfaces in vast subsurface oceans that rival the water reserves of entire terrestrial worlds. These internal seas represent one of the most intriguing possibilities in astrobiology: the prospect that life could flourish in perpetual darkness, sustained by heat sources that have nothing to do with stellar radiation. The key to understanding habitability on rogue planets lies in recognizing the various mechanisms that can generate and maintain heat within planetary interiors long after ejection from their parent star systems. The most universal of these heat sources is radiogenic heating, the steady decay of radioactive elements like uranium, thorium, and potassium that were incorporated into the planet during its formation. This process provides a continuous, if gradually diminishing, source of internal energy that can persist for billions of years. For a rogue planet with Earth-like composition and mass, radiogenic heating alone can maintain subsurface liquid water for geological timescales. The planet's outer layers would freeze solid within a few million years of ejection, creating an insulating shell of ice that helps retain internal heat. Beneath this frozen crust, temperatures could remain above freezing at depths of several miles, creating conditions suitable for vast underground oceans. The physics of heat retention in rogue planets involves a delicate balance between heat generation, conduction, and loss to space. Larger rogue planets have significant advantages in this regard, as their greater mass provides more radioactive material for heat generation, while their lower surface area-to-volume ratio reduces the rate of heat loss. A rogue planet with twice Earth's radius could maintain subsurface oceans for much longer periods than smaller worlds, potentially supporting stable aquatic environments for the entire age of the galaxy. Tidal heating represents another potential energy source for rogue planets that retained moons during their ejection from stellar systems. The gravitational interaction between a rogue planet and its satellite can generate internal friction as tidal forces flex the planet's interior, converting orbital energy into heat. This process is responsible for maintaining subsurface oceans on Jupiter's moon Europa despite its location in the cold outer solar system, and could operate even more effectively in rogue planet systems, where the satellite orbits are not influenced by nearby stellar gravity. The composition and structure of rogue planet oceans would differ significantly from Earth's surface seas. Without atmospheric pressure or surface exchange processes, these subsurface waters would exist in direct contact with the rocky or icy materials of the planet's interior. This intimate contact could create chemically rich environments where dissolved minerals and organic compounds concentrate over geological timescales, potentially providing the chemical complexity necessary for life to emerge and evolve. Hydrothermal activity could play a crucial role in making rogue planet oceans habitable. If radiogenic or tidal heating is sufficient to maintain partial melting of the rocky interior, hydrothermal vents could form at the bottom of subsurface seas, providing localized sources of heat, chemical energy, and complex organic molecules. These environments would closely resemble the deep-sea hydrothermal vents on Earth that support thriving ecosystems completely independent of solar energy. The possibility of atmospheric retention on rogue planets depends strongly on their mass and composition. Smaller rocky rogue planets would quickly lose any atmosphere to space after ejection from their stellar systems, leaving their surfaces exposed to the vacuum of interstellar space. However, massive rogue planets, particularly those with substantial hydrogen-helium atmospheres, like gas giants, could retain significant atmospheric envelopes that provide additional insulation and maintain higher surface pressures. Super-Earth rogue planets, worlds with masses several times that of Earth, represent particularly intriguing targets for habitability studies. These planets could potentially retain thin atmospheres of carbon dioxide, water vapor, or other volatile compounds that would create greenhouse effects, helping to maintain surface temperatures closer to the freezing point of water. While still extremely cold by terrestrial standards, Such conditions might allow for unique forms of surface chemistry and possibly even specialized forms of life adapted to low-temperature environments. The timeline for maintaining habitable conditions on rogue planets extends far beyond what might be possible for planets orbiting stars. While stellar-heated worlds face eventual challenges as their host stars evolve and change brightness over billions of years, rogue planets powered by internal heat sources could potentially maintain stable conditions for tens of billions of years, longer than the current age of the universe. Recent discoveries of extremophile organisms on Earth have expanded our understanding of the environmental conditions that can support life. Organisms have been found thriving in environments with temperatures near freezing, in the absence of sunlight, and in water with extreme chemical compositions, all conditions that might be common in rogue planet subsurface oceans. These findings suggest that the emergence of life in such environments is not only possible, but perhaps even likely given sufficient time and chemical complexity. The detection of life on rogue planets would require different strategies than those being developed for exoplanets orbiting stars. Since rogue planets emit virtually no detectable light and have no atmospheric signatures visible to current telescopes, evidence for biological activity would likely need to come from direct exploration missions, or from detecting unusual chemical signatures in interstellar space that might originate from rogue planet atmospheres. The implications of discovering life on rogue planets would be profound for astrobiology and our understanding of life's prevalence in the universe. If life can emerge and thrive in the perpetual darkness of interstellar space, then the number of potentially habitable worlds in our galaxy might be far larger than current estimates, based only on planets in stellar habitable zones. Now, close your eyes and picture how all of this might look. Imagine descending through miles of solid ice on a rogue planet, deeper and deeper until the ice becomes slush, and then liquid water warmed by the planet's slowly beating heart of radioactive decay. Picture vast caverns filled with water that has never seen sunlight, possibly teeming with life forms that evolved in eternal darkness, sustained by the planet's own internal energy as it wanders forever through the space between stars. The extreme physics of lonely worlds. The physical conditions on rogue planets represent some of the most extreme environments in the galaxy, where the normal rules that govern planetary atmospheres, surface processes, and thermal evolution are pushed to their absolute limits. These worlds exist in a state of perpetual winter that makes Earth's ice ages seem tropical by comparison. Yet beneath their frozen surfaces, complex physics creates possibilities for unexpected warmth and activity. Surface temperatures on rogue planets depend primarily on their internal heat sources and the insulating properties of their atmospheres or surface materials. For a rocky rogue planet with no atmosphere, surface temperatures would quickly equilibrate to the temperature of interstellar space, approximately -450 degrees Fahrenheit, or just a few degrees above absolute zero. At these temperatures, virtually all chemical processes cease, and even the hardiest materials become brittle and prone to fracturing under thermal stress. However, the presence of an atmosphere, even a thin one, can dramatically alter surface conditions through greenhouse effects and thermal inertia. Carbon dioxide, water vapor, and other greenhouse gases can trap outgoing infrared radiation, maintaining surface temperatures significantly above the cosmic background. A rogue planet with a substantial carbon dioxide atmosphere might maintain surface temperatures similar to those found on Mars today, still far below freezing, but potentially warm enough for specialized chemical processes. The atmospheric dynamics of rogue planets would differ fundamentally from those of planets orbiting stars. Without stellar heating to drive temperature differences between day and night sides or between equatorial and polar regions, atmospheric circulation would be powered entirely by internal heat sources. This could create unique weather patterns dominated by convection from below rather than radiative heating from above, possibly resulting in global circulation patterns that are more uniform and predictable than those found on stellar-heated worlds. Massive rogue planets retain their primordial atmospheres of hydrogen and helium, creating conditions more similar to gas giant planets than terrestrial worlds. These thick atmospheres provide excellent insulation, allowing internal heat to maintain relatively warm conditions in the deep atmospheric layers. The atmospheric pressure at depth could be sufficient to maintain liquid water, creating a unique class of aerial habitable zones suspended within gas giant atmospheres. The magnetic fields of rogue planets play crucial roles in shaping their interaction with the interstellar medium. Planets with active dynamos in their metallic cores generate magnetic fields that deflect cosmic rays and charged particles, protecting any subsurface oceans or atmospheric chemistry from harmful radiation. The strength and configuration of these magnetic fields depend on the planet's rotation rate, internal structure, and thermal evolution, creating a diverse range of magnetospheric environments. Geological processes on rogue planets are driven primarily by internal heat sources rather than external forces like tidal interactions with nearby bodies or thermal cycling from stellar radiation. Radioactive decay provides a steady but gradually diminishing heat source that can maintain tectonic activity for billions of years, particularly in large rogue planets with substantial uranium and thorium reserves. This internal heating can drive volcanism, mountain building, and other geological processes that reshape planetary surfaces over geological timescales. The absence of external heating sources creates unique opportunities for studying planetary thermal evolution in isolation. Rogue planets serve as natural laboratories for understanding how worlds cool and evolve when influenced only by their internal energy sources, providing insights into processes that are difficult to study in the complex gravitational and radiative environments of stellar systems. Crystallization and phase transition processes on rogue planets operate under conditions rarely encountered elsewhere in the galaxy. The extreme cold can create unusual forms of ice with different crystal structures than those found at higher temperatures, while the gradual cooling over billions of years allows for the formation of particularly large and well-ordered crystal structures. These materials might have unique properties that affect everything from seismic wave propagation to the chemistry of subsurface oceans. The space environment surrounding rogue planets is remarkably quiet compared to the dynamic conditions near stars. Without stellar wind, coronal mass ejections, or intense ultraviolet radiation, the immediate vicinity of rogue planets is dominated by the gentle flow of the interstellar medium and occasional interactions with cosmic rays or interstellar dust grains. This stable environment could allow for the accumulation of unusual atmospheric compositions or the preservation of volatile compounds that would be quickly destroyed in stellar systems. Thermal gradients within rogue planets can be extreme, with surface temperatures near absolute zero, while internal temperatures may reach thousands of degrees in the deep interior. These gradients drive convection patterns that transport heat from the core to the surface, creating complex internal dynamics that influence everything from magnetic field generation to the distribution of volatile compounds. Understanding these thermal structures requires sophisticated models that account for radiogenic heating, thermal conduction, and convective heat transport in materials under extreme pressure and temperature conditions. The long-term evolution of rogue planets involves gradual cooling and crystallization, as internal heat sources slowly decay over billions of years. This process is not uniform. Different regions of the planet cool at different rates depending on their composition, distance from heat sources, and thermal conductivity. The result is a complex internal structure that evolves continuously over cosmic timescales, potentially creating and destroying habitable environments as thermal conditions change. Some rogue planets may experience periodic reheating events if they encounter other massive objects during their wandering through the galaxy. Close passages with stars, collisions with asteroids or comets, or gravitational interactions with other rogue planets could temporarily increase internal heating through tidal effects or impact energy, creating brief periods of enhanced geological activity or atmospheric outgassing. The study of rogue planet physics also provides insights into fundamental questions about planetary formation and evolution. These worlds represent natural experiments in planetary science, showing how worlds behave when isolated from the complex interactions that characterize planets in stellar systems. Understanding their physical properties helps astronomers develop more complete theories of planetary processes that apply across the full range of environments found in the galaxy. Clusters in the cosmic dark. Among the most surprising discoveries in rogue planet astronomy is the existence of rogue planet clusters, loose associations of free-floating worlds that travel through interstellar space together, creating temporary neighborhoods in the otherwise empty regions between stars. These cosmic communities challenge our understanding of how rogue planets form and evolve, suggesting that the ejection process from stellar systems can be far more complex and organized than previously imagined. The first evidence for rogue planet clustering came from observations of young star-forming regions, where astronomers discovered groups of planetary mass objects that appeared to share similar motions through space. Rather than being randomly distributed throughout the stellar nursery, these objects seemed to be moving together in loose associations that contain dozens of individual worlds. The discovery suggested that some rogue planets might form not as isolated objects, but as members of gravitationally bound groups. Computer simulations of planetary system evolution have revealed several mechanisms that could produce rogue planet clusters. During periods of dynamical instability in young stellar systems, multiple planets can be ejected in rapid succession through a cascade of gravitational interactions. If these ejection events occur over relatively short timescales, the ejected planets may retain similar velocities and directions, causing them to travel through interstellar space as a dispersed group for millions of years before eventually separating. The Orion Nebula, one of the nearest and most intensively studied star-forming regions, contains several apparent rogue planet clusters that provide insights into this phenomenon. These associations typically span several light-years in diameter and contain anywhere from a few dozen to several hundred planetary mass objects. The objects within each cluster share similar proper motions, the slow drift across the sky that indicates their common direction of travel through space. Spectroscopic observations of cluster members reveal important clues about their formation history. Many rogue planets within the same cluster show similar chemical compositions, suggesting they formed from the same reservoir of gas and dust, or originated from the same stellar system. This chemical fingerprinting technique allows astronomers to trace the relationships between cluster members and potentially identify their common origin points. The dynamics of rogue planet clusters involve a delicate balance between the weak gravitational attraction between cluster members and the disruptive effects of encounters with other objects. While individual rogue planets have far too little mass to gravitationally bind themselves into permanent associations, the collective gravity of an entire cluster can provide some cohesion that extends the lifetime of the group beyond what would be expected for completely unbound objects. Typical rogue planet clusters expand slowly over time as the random velocities of individual members gradually overcome the weak collective gravity of the group. Cluster sizes grow at rates of approximately 1 mile per second, meaning that a cluster that is initially a few light years across will double in size every few million years. This expansion eventually leads to the dissolution of the cluster as members disperse throughout the local interstellar medium. The age determination for rogue planet clusters relies on measuring their current size and expansion rate, then extrapolating backward to estimate when the cluster members were more tightly bound together. Most observed clusters appear to be relatively young, with ages ranging from 1 to 10 million years. Though older clusters may exist, but be difficult to identify due to their large size and low member density, encounters with molecular clouds, stellar systems, or other massive objects can dramatically affect cluster evolution by accelerating the dispersal process, or, in rare cases, temporarily compressing the cluster and extending its lifetime. When a rogue planet cluster passes through the gravitational field of a star or stellar system, differential tidal forces can stretch the cluster along its direction of motion, potentially stripping away the most loosely bound members while concentrating the remaining objects into a more compact configuration. The discovery of rogue planet clusters has implications for understanding the early evolution of our own solar system. Some models suggest that our solar system may have formed as part of a larger stellar cluster that included other planetary systems undergoing similar dynamical evolution. If our solar system ejected planets during its early history, those worlds might now be traveling through space as part of a dispersed cluster that includes rogue planets from other nearby stellar systems. Binary and multiple rogue planet systems represent a special case of clustering on the smallest scales. These systems consist of 2 or more rogue planets orbiting around their common center of mass, held together by their mutual gravitational attraction, despite being ejected from their parent stellar system. The formation of binary rogue planets requires very specific conditions during the ejection process that allow 2 planets to escape together while retaining their gravitational bond. The orbital characteristics of binary rogue planet systems provide information about the violence of the ejection process and the original configuration of the planetary system from which they escaped. Wide binary systems with separations of hundreds or thousands of astronomical units are more easily disrupted during ejection, while tight binaries with separations comparable to the Earth-Moon distance are more likely to survive the transition to free-floating status. Theoretical models predict that binary rogue planet systems should be relatively rare, comprising perhaps 1% or less of the total rogue planet population. However, their detection through gravitational microlensing surveys could be enhanced compared to single planets due to their more complex lensing signatures, potentially making them appear more common in observational samples than they actually are in the galaxy. The study of rogue planet clusters provides unique opportunities for comparative planetology on an interstellar scale. By examining multiple worlds that likely formed in the same environment and underwent similar evolutionary histories, astronomers can identify which planetary characteristics are fundamental properties of the formation process and which result from specific environmental conditions or chance events. Future surveys with next-generation telescopes will dramatically improve our ability to identify and characterize rogue planet clusters. The enhanced sensitivity and wide field capabilities of upcoming instruments will enable the detection of fainter cluster members and provide better constraints on cluster membership through improved proper motion measurements and spectroscopic characterization. The long-term fate of rogue planet clusters depends on their encounters with the galactic environment over hundreds of millions of years. Clusters that formed in the dense central regions of the galaxy may experience more frequent disruptive encounters than those in the sparse outer regions where our solar system resides. Understanding this environmental influence on cluster evolution will help astronomers predict the current distribution of dispersed rogue planet populations throughout the Milky Way. Windows into planetary formation. Rogue planets serve as unique laboratories for understanding planetary formation processes, offering insights into how worlds develop that cannot be obtained from studying planets that remain bound to their parent stars. These cosmic outcasts preserve evidence of their formation conditions in their compositions, structures, and physical properties, creating a fossil record of planetary birth that spans billions of years of galactic history. The chemical composition of rogue planets reflects the materials available in their birth environments, providing direct information about the conditions in protoplanetary disks at the time of their formation. Unlike planets that continue to interact with their host stars through atmospheric escape, tidal interactions, or stellar evolution effects, rogue planets maintain their original compositions virtually unchanged after ejection from their parent systems. Spectroscopic studies of the atmospheres and surface materials of rogue planets reveal isotopic ratios and elemental abundances that can be compared with theoretical models of stellar nucleosynthesis and galactic chemical evolution. Each rogue planet carries within its composition a signature of the stellar generations that contributed material to its formation region, creating a chemical fingerprint that traces back to the specific time and place in galactic history when that world came into being. The size distribution of rogue planets provides crucial constraints on the mechanisms that dominate planetary formation in different mass regimes. Current observations suggest that lower-mass rogue planets are more abundant than massive gas giants, indicating that the core accretion process that builds terrestrial planets operates more efficiently than the gravitational instability mechanism that can rapidly form giant planets. This mass distribution offers insights into the relative importance of these competing formation pathways across different stellar environments. Rocky rogue planets preserve information about the solid materials available in their birth systems, including the abundance of water ice, organic compounds, and refractory minerals that determine planetary composition. The presence or absence of certain volatile compounds in rogue planet atmospheres can indicate whether these worlds formed inside or outside the snowline in their original systems. The distance from their parent star where water ice could condense in the protoplanetary disk. Gas giant rogue planets provide complementary information about the conditions in the outer regions of planetary systems where these massive worlds typically form. Their atmospheric compositions reveal details about the temperature and pressure conditions in their birth environments, while their internal structures preserve information about the timing and efficiency of gas accretion during the final stages of planetary formation. The discovery of rogue planets with unusual compositions or structures provides evidence for exotic formation scenarios that may be rare in bound planetary systems. Some rogue planets may have formed through direct collapse of gas clouds without going through the traditional core accretion process, while others might represent the cores of disrupted gas giants that lost their atmospheric envelopes during violent ejection events. Comparative studies of rogue planets with different ages provide insights into how planetary formation processes have evolved over cosmic time. Older rogue planets formed when the galaxy had different chemical composition and stellar populations than exist today, potentially showing systematic differences in their compositions that reflect the changing galactic environment over billions of years. The orbital characteristics of binary rogue planet systems preserve information about the architecture of their parent planetary systems before ejection occurred. The separation and eccentricity of binary components can be used to constrain the original orbital configuration and the dynamics of the ejection process, providing indirect observations of planetary system evolution that would be impossible to obtain through other means. Rogue planets also serve as natural experiments in planetary evolution under extreme conditions. Their thermal histories, determined entirely by internal heat sources after ejection, demonstrate how worlds evolve in the absence of stellar heating. These isolated evolutionary pathways help astronomers understand which planetary characteristics are fundamental properties of formation and which result from ongoing stellar interactions. The absence of atmospheric escape processes on many rogue planets means they retain their original volatile inventories, providing information about the delivery of water, organic compounds, and other life-essential materials during planetary formation. This preserved record of volatile accretion helps constrain models of how habitable worlds acquire the materials necessary for life. Studies of rogue planet populations in different regions of the galaxy reveal how local environmental conditions affect planetary formation efficiency and outcomes. Regions with different stellar densities, metallicities, or dynamical environments may produce systematically different populations of rogue planets, providing insights into the environmental factors that control planetary system architecture. The statistical properties of rogue planet populations, including their mass functions, spatial distributions, and kinematic properties, provide powerful tests of theoretical models of planetary formation and evolution. Large-scale surveys that detect thousands of rogue planets will enable precision comparisons between observations and simulations, potentially revealing new physics or formation mechanisms that current models do not include. Rogue planets may also preserve evidence of their original planetary system configurations through their physical properties and chemical compositions. Worlds that formed in systems with different numbers of giant planets, different disk masses, or different stellar multiplicities may show systematic differences that can be identified through careful statistical analysis of large samples. The detection of intact moon systems around rogue planets provides particularly valuable information about satellite formation processes and the conditions required for moons to survive planetary ejection events. These rare systems offer insights into the tidal evolution of satellite orbits and the role of planetary magnetospheres in protecting satellite atmospheres from erosion. Future missions that could visit nearby rogue planets would provide unprecedented detailed information about planetary formation processes. Direct measurements of surface compositions, internal structures, and thermal properties would complement remote observations and provide ground truth for theoretical models of how worlds form and evolve in different environments. The study of rogue planets ultimately contributes to a more complete understanding of planetary formation that encompasses the full range of outcomes possible in stellar systems. By examining both the worlds that remain bound to their stars and those that have been cast into interstellar space, astronomers can develop more comprehensive theories that explain the diversity of planetary systems observed throughout the galaxy. Now, close your eyes and picture how all of this might look. Imagine the galaxy as a vast laboratory where billions of planetary systems have conducted experiments in world-building over cosmic time. Each rogue planet drifting through the darkness carries with it the results of one of these experiments, preserving in its composition and structure the secrets of how worlds are born among the stars. The galaxy's hidden census. The implications of rogue planet discoveries extend far beyond simple curiosity about wandering worlds, fundamentally reshaping our understanding of how common planets are in the universe and what this means for the prospects of life beyond Earth. If current estimates prove correct, rogue planets may represent the dominant form of planetary matter in our galaxy, outnumbering the familiar worlds that orbit stars by factors of 10 or more. This hidden population of planets challenges traditional definitions of planetary systems and habitable zones. The concept of a habitable zone, the region around a star where liquid water can exist on a planetary surface, becomes largely irrelevant for worlds that generate their own heat through internal processes. Instead, habitability for rogue planets depends on factors like planetary mass, composition, and the efficiency of internal heat generation and retention. The sheer number of rogue planets suggests that planet formation is an even more prolific process than previously recognized. If stellar systems regularly eject significant fractions of their planetary populations during early dynamical evolution, then the total amount of solid material that gets processed into planetary form may be much larger than estimates based only on bound planets would suggest. Understanding the true abundance of rogue planets has important implications for calculating the probability of life in the galaxy. If these worlds can indeed harbor habitable subsurface oceans or atmospheric environments, then the number of potentially life-bearing worlds may be orders of magnitude larger than current estimates that focus primarily on planets in stellar habitable zones. The galactic distribution of rogue planets provides insights into the history of star formation and planetary system evolution throughout the Milky Way. Regions that experienced intense star formation in the past may now contain higher concentrations of ancient rogue planets, ejected during the chaotic early epochs of galactic evolution. These patterns could help astronomers map the galaxy's formation history through the distribution of its wandering worlds. Rogue planets also represent a significant reservoir of heavy elements: carbon, oxygen, silicon, iron, and other materials that are essential for rocky planet formation and potentially for life. The total mass locked up in rogue planets may rival or exceed the mass contained in bound planetary systems, suggesting that a substantial fraction of the galaxy's heavy elements exists in these dark, wandering worlds. The kinematic properties of rogue planet populations provide information about the dynamical history of the galactic disk and the processes that mix material between different stellar populations. Rogue planets ejected from stellar systems billions of years ago may now be distributed throughout the galaxy in ways that trace the large-scale motions and interactions that have shaped galactic structure over cosmic time. Recent theoretical work suggests that rogue planets may play important roles in galactic chemical evolution by transporting processed materials between different regions of the galaxy. If these worlds retain substantial atmospheres or surface volatiles, they could carry complex organic compounds or even biological materials across vast distances, potentially facilitating the spread of life between stellar systems through a process sometimes called panspermia. The discovery that rogue planets are common also has implications for the search for extraterrestrial intelligence. If technological civilizations can arise on worlds that don't orbit stars, they might develop very different approaches to energy generation, space exploration, and interstellar communication than civilizations that evolved in stellar systems. Such societies might be much harder to detect using traditional SETI methods that focus on signals from stellar systems. The economic and resource implications of widespread rogue planets become relevant as humanity develops more advanced space exploration capabilities. These worlds could serve as stepping stones for interstellar exploration, providing sources of water, minerals, and other materials for spacecraft traveling between star systems. A galaxy filled with rogue planets might be much more accessible to future spacefaring civilizations than one where resources are concentrated only around stars. Understanding rogue planet populations also helps calibrate theories of planetary formation and evolution that are applied to observations of exoplanets around other stars. If ejection processes are common, then the planets we observe in other stellar systems may represent only a fraction of the worlds that originally formed there, requiring adjustments to formation models and predictions about planetary system architecture. The environmental impact of rogue planets on the interstellar medium remains an active area of research. These worlds may affect the chemistry and thermal structure of interstellar gas clouds through gravitational interactions, atmospheric outgassing, or magnetic field effects. Large populations of rogue planets could collectively influence the conditions for star formation in molecular clouds over cosmic timescales. Climate modeling for rogue planets requires new theoretical frameworks that account for the unique thermal and atmospheric conditions on worlds powered entirely by internal heat sources. These models help determine which rogue planets might maintain habitable conditions and for how long, providing targets for future observational searches for signs of life or atmospheric activity. The long-term evolution of rogue planet populations involves complex interactions with the galactic environment, including encounters with molecular clouds, stellar systems, and other massive objects that can alter orbital trajectories or even capture rogue planets into new stellar systems. Understanding these processes helps predict how rogue planet distributions will change over the remaining lifetime of the galaxy. Future space missions dedicated to studying rogue planets will require new technologies and observational strategies adapted to their unique properties. Unlike exoplanets that can be studied using starlight, rogue planets must be detected and characterized through their own thermal emission, gravitational effects, or through direct exploration missions that can reach nearby examples. The study of rogue planets ultimately contributes to a more complete picture of planetary demographics in the universe, revealing that worlds are far more numerous and diverse than traditional surveys of stellar systems would suggest. This expanded view of planetary abundance has profound implications for astrobiology, cosmology, and our understanding of humanity's place in a galaxy that may contain trillions of hidden worlds drifting silently through the cosmic dark. If this peaceful view of the cosmos brings you calm, consider returning here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars. Conclusion: endless wanderers in the night. As our journey through the realm of rogue planets draws to a close, the profound implications of these cosmic wanderers settle into perspective like starlight, gradually revealing the depths of a clear night sky. These worlds represent far more than astronomical curiosities. They embody a fundamental aspect of planetary existence that challenges everything we once thought we knew about the distribution and nature of worlds in our galaxy. The trillions of rogue planets drifting through interstellar space outnumber the familiar worlds that orbit stars, creating a hidden majority of planetary matter that exists in perpetual darkness, yet may harbor the conditions necessary for life. Their existence transforms our understanding of habitability, from a concept tied exclusively to stellar radiation to one that embraces the possibilities inherent in internal planetary processes and the remarkable resilience of life in extreme environments. These wandering worlds carry within their frozen surfaces and potentially liquid interiors the complete history of planetary formation and evolution, preserving chemical signatures and physical structures that tell the story of how worlds are born and how they change over cosmic time. Each rogue planet serves as a time capsule, maintaining evidence of the conditions that existed in its birth system billions of years ago, when the galaxy was younger and stellar formation proceeded at a much more rapid pace. The gentle motion of rogue planets through interstellar space embodies a kind of cosmic patience that spans geological eras, moving at speeds of tens of miles per second, yet appearing motionless against the backdrop of distant stars. These worlds demonstrate the vast scales of time and distance that govern galactic evolution. A rogue planet ejected from a stellar system near the galactic center 8 billion years ago might now be approaching the outer spiral arms, having traveled hundreds of thousands of light-years in its lonely journey through space. The possibility that some rogue planets maintain subsurface oceans heated by radioactive decay or tidal interactions suggests that the galaxy may contain countless hidden biospheres, each evolving in isolation from the rest of the universe. Life forms that might exist in these perpetually dark seas would represent completely independent experiments in biological evolution, potentially developing along pathways that have no parallel among the life forms that evolved under stellar radiation. The upcoming missions and surveys that will dramatically expand our knowledge of rogue planet populations promise to reveal whether these worlds are as numerous as current estimates suggest, and whether their properties match the theoretical predictions derived from models of planetary formation and evolution. The Nancy Grace Roman Space Telescope's comprehensive microlensing survey will provide the first complete census of free-floating planets across a wide range of masses, potentially discovering thousands of new worlds and refining our understanding of their galactic distribution. As detection techniques improve and our understanding of rogue planet properties deepens, these worlds may become accessible targets for future exploration missions. The closest rogue planets to our solar system could be nearer than the nearest stars, making them potentially reachable with advanced propulsion technologies that future generations might develop. Such missions would provide unprecedented insights into planetary science and possibly even astrobiology if any of these worlds prove to harbor life. The study of rogue planets also offers unique perspectives on the long-term fate of our own solar system and the planets within it. As our sun evolves over the next several billion years, the changing stellar environment may destabilize planetary orbits, potentially ejecting some worlds into interstellar space, where they would join the vast population of cosmic nomads already wandering through the galaxy. The existence of rogue planet clusters and binary systems demonstrates that even in the apparent isolation of interstellar space, gravitational relationships can persist, creating temporary communities of worlds that travel together through the cosmic dark. These associations provide insights into the violence and complexity of planetary ejection processes, while suggesting that the transition from bound to free-floating status may preserve more structure and organization than previously thought possible. The chemical diversity of rogue planets reflects the full range of stellar environments and formation conditions that have existed throughout galactic history. From worlds formed in the metal-rich inner regions of the galaxy to those that condensed from the primordial materials available during earlier epochs of cosmic evolution, rogue planets sample the complete spectrum of planetary compositions and provide natural laboratories for studying how different formation environments affect planetary properties. The thermal evolution of rogue planets over billions of years demonstrates the remarkable ability of worlds to maintain internal heat sources long after separation from their parent stars. The gradual cooling process that these worlds undergo reveals fundamental aspects of planetary physics, while creating environments that may transition between habitable and inhospitable states multiple times over cosmic history. As we consider the vast numbers of rogue planets that may exist in our galaxy, their potential for harboring life, and their role in preserving the history of planetary formation, these worlds invite us to expand our perspective on what constitutes a planetary system and where we might search for life beyond Earth. They remind us that the universe is far more rich and complex than surveys of stellar systems alone would suggest, filled with hidden worlds that pursue their own evolutionary pathways in the spaces between stars. The gentle drift of rogue planets through the galaxy continues as you settle into sleep. These cosmic wanderers pursuing their eternal journeys through interstellar space at speeds that cross continents in minutes yet require millions of years to traverse the distances between stars. In the vast quiet of space, where temperature approaches absolute zero and no stellar wind disturbs the ancient ice, these worlds maintain their silent vigil, carrying within their cores the slowly fading warmth of their formation, and perhaps, in hidden seas beneath their frozen surfaces, the delicate chemistry of life itself. Their stories unfold over timescales that dwarf human history, yet their existence touches on fundamental questions about the nature of planets, the prevalence of life, and the deep structure of our galaxy. As you drift toward sleep, let the image of these wandering worlds bring peace. Countless spheres of rock and ice pursuing their patient paths through the cosmic night, each one a world unto itself, complete and self-contained, moving through the darkness toward destinations unknown, carrying within themselves all the materials and energy needed for their own quiet existence in the vast spaces between the stars. The galaxy turns slowly around its distant center, and with it, trillions of rogue planets continue their eternal dance through the interstellar medium, invisible wanderers in the cosmic dark. Each one a reminder that the universe contains far more worlds than we can see, far more possibilities than we have yet imagined, far more stories than we will ever fully know. In this gentle understanding, find rest, knowing that even in the apparent emptiness of space, worlds drift silently by, patient and enduring, carrying their secrets through the endless night. The thermal architecture of wandering worlds deep within rogue planets. Heat flows according to physical laws that create complex thermal architectures, unlike anything found on worlds that bask in stellar radiation. The internal structure of these wandering spheres resembles a series of nested shells, each with its own temperature regime and physical properties, creating environments that range from the extreme cold of interstellar space at the surface to temperatures rivaling those found in stellar cores at the very center. The outermost layer of a typical rogue planet consists of a frozen crust that can extend dozens of miles into the interior. This shell of solid ice and rock serves as an insulating blanket that traps heat generated by deeper layers, creating a greenhouse effect that operates in reverse. Instead of atmospheric gases trapping solar radiation, solid materials trap geothermal energy radiating outward from the planet's core. The composition of this crust varies dramatically depending on the planet's formation history and original atmospheric inventory. Water ice dominates the surface composition of many rogue planets, frozen into crystal structures that can remain stable for billions of years at the temperatures found in interstellar space. These ice formations create landscapes of stunning beauty, with crystalline formations stretching across continents, sculpted by the planet's rotation, gravitational forces, and the occasional impact from interstellar debris. The ice itself becomes a historical record, with different layers preserving atmospheric compositions from different epochs of the planet's evolution. Beneath the frozen crust, temperatures rise gradually due to heat conducted upward from radioactive decay in the planet's interior. At depths of several miles, conditions may become warm enough for liquid water to exist, creating the possibility of vast subsurface oceans that dwarf Earth's surface seas in their volume and complexity. These buried oceans represent some of the most stable aquatic environments in the galaxy, protected from cosmic radiation by miles of overlying ice and maintained at constant temperatures by the planet's internal heat sources. The interface between the frozen crust and liquid ocean creates unique chemical environments where complex organic chemistry can occur over geological timescales. Dissolved minerals from the rocky interior mix with organic compounds that may have been present since the planet's formation, creating chemical soups that could support the emergence and evolution of life forms completely adapted to high-pressure, lightless environments. Deeper within rogue planets, the rocky mantle experiences temperatures and pressures that drive slow but continuous geological processes. Convection currents in the mantle transport heat from the core toward the surface, creating patterns of circulation that can persist for billions of years. These convective motions generate the planet's magnetic field through dynamo action in the metallic core, creating protective magnetospheres that shield surface and subsurface environments from harmful cosmic radiation. The core of a rogue planet represents the ultimate source of its internal energy, where radioactive elements like uranium, thorium, and potassium undergo steady decay that releases heat at rates determined by fundamental nuclear physics. The half-lives of these elements, measured in billions of years, ensure that rogue planets can maintain significant internal heating for periods comparable to the current age of the universe. Larger rogue planets, with more radioactive material in their cores, can sustain higher internal temperatures for longer periods than smaller worlds. Thermal modeling of rogue planet interiors reveals that these worlds can maintain internal liquid water for periods extending far beyond the main sequence lifetimes of typical stars. While planets orbiting stars face inevitable changes in their thermal environments as their host stars evolve, rogue planets powered by radioactive decay experience only gradual, predictable cooling over cosmic timescales. This thermal stability could provide the long-term environmental consistency that complex life requires to evolve and diversify. The heat flow patterns within rogue planets create temperature gradients that drive chemical processes throughout their interiors. Near the core mantle boundary, temperatures may be sufficient to maintain partial melting of rocky materials, creating magma chambers and volcanic processes that operate without any connection to surface phenomena. These deep volcanic systems could create hydrothermal environments where the chemistry of life might emerge and flourish in complete independence from surface conditions. Pressure conditions within rogue planets reach extremes that compress matter into exotic phases rarely encountered elsewhere in nature. At the boundary between the metallic core and rocky mantle, pressures may exceed those found at the center of the Earth, creating conditions where ordinary materials exhibit unusual properties. These extreme environments serve as natural laboratories for studying matter under conditions that cannot be replicated in terrestrial experiments. The thermal evolution of rogue planets over cosmic time involves complex feedback mechanisms between heat generation, heat transport, and heat loss that determine how long these worlds can maintain habitable conditions. Computer models suggest that the most massive rogue planets could sustain subsurface oceans for periods exceeding 100 billion years, far longer than the current age of the universe, and extending well beyond the era when star formation will cease in our galaxy. Variations in rogue planet composition create diverse thermal architectures that support different types of internal environments. Rocky rogue planets with high concentrations of radioactive elements can maintain higher internal temperatures than worlds with lower radioactive inventories, while ice-rich rogue planets may have thicker insulating layers that more effectively retain internal heat. These compositional differences create a spectrum of thermal environments that could support different forms of life or geological activity. The interaction between thermal processes and magnetic field generation in rogue planets creates dynamic internal environments that change over geological timescales. As the core slowly cools and solidifies, the strength and configuration of the magnetic field evolve, potentially affecting the planet's ability to retain any remaining atmosphere or protect surface materials from cosmic radiation. Understanding these long-term changes helps predict how habitability might vary over the billions of years that rogue planets wander through interstellar space. Surface thermal processes on rogue planets operate according to principles completely different from those found on planets heated by stellar radiation. Without day-night temperature cycles or seasonal variations, thermal evolution depends entirely on heat, conducted from the interior, and the insulating properties of surface materials. These conditions create unique opportunities for studying planetary thermal physics in isolation from the complex radiative processes that dominate surface temperatures on planets orbiting stars. Now, close your eyes and picture how all of this might look. Imagine descending through the layers of a rogue planet, from the frozen surface through gradually warmer ice formations, into liquid regions where ancient waters flow in eternal darkness, and finally into the rocky depths where radioactive elements provide the gentle heartbeat of heat that sustains this hidden world as it drifts silently through the cosmic night. Magnetic shields in the cosmic void. The magnetic fields generated by rogue planets create invisible protective barriers that extend far into space, forming magnetospheres that serve as shields against the harsh radiation environment of interstellar space. These magnetic environments represent some of the most stable and long-lasting magnetospheres in the galaxy, persisting for billions of years without the disruptive influence of stellar winds or coronal mass ejections that constantly buffet planets orbiting active stars. The generation of magnetic fields in rogue planets follows the same basic physical principles that operate in all planetary bodies with molten metallic cores. As heat from radioactive decay drives convection in the planet's iron-rich core, the motion of electrically conducting material creates electric currents that generate magnetic fields through dynamo action. The strength and configuration of these fields depend on the planet's rotation rate, internal structure, and thermal evolution over cosmic time. Rogue planet magnetospheres differ fundamentally from those found around planets in stellar systems because they interact primarily with the tenuous interstellar medium rather than dense stellar winds. The interstellar medium contains roughly 1 atom per cubic centimeter, an environment so sparse that it barely registers as matter by terrestrial standards. However, over the vast scales of planetary magnetospheres, which can extend hundreds of thousands of miles into space, even this tenuous material creates detectable interactions with planetary magnetic fields. The boundary between a rogue planet's magnetosphere and the surrounding interstellar medium, called the magnetopause, represents one of the most stable plasma boundaries in nature. Unlike the dynamic magnetopauses of planets orbiting stars, which constantly expand and contract in response to variable stellar wind pressure, rogue planet magnetopauses maintain relatively constant shapes and sizes determined by the steady pressure of the interstellar medium and the planet's magnetic field strength. Charged particles from cosmic rays, high-energy protons, and atomic nuclei that travel through the galaxy at nearly the speed of light interact with rogue planet magnetospheres in ways that create unique radiation environments around these worlds. Most cosmic rays are deflected by the magnetic field, but some become trapped in radiation belts that circle the planet, creating zones of enhanced radiation similar to the Van Allen belts around Earth, but potentially much more stable and long-lasting. The aurora phenomena that occur in rogue planet magnetospheres differ significantly from the familiar northern and southern lights seen on Earth. Without intense particle streams from a nearby star, rogue planet auroras result primarily from interactions with cosmic rays and the sparse charged particles of the interstellar medium. These auroral displays would be much fainter than terrestrial auroras, but could persist continuously for millions of years, creating ghostly curtains of light that dance in the planet's magnetic field lines. The magnetic field strength of rogue planets provides crucial information about their internal structure and thermal evolution. Planets with active dynamos generated by vigorous core convection produce stronger magnetic fields than worlds with sluggish or inactive cores. Measurements of magnetic field strength could therefore serve as indirect probes of rogue planet interior conditions, revealing which worlds maintain the internal heat sources necessary to drive geological activity and potentially support subsurface oceans. Some rogue planets may have magnetic field configurations that differ dramatically from the relatively simple dipolar fields found around most planets in stellar systems. Without the organizing influence of stellar magnetic fields or the complex plasma environments created by stellar winds, rogue planet magnetic fields can evolve into complex multipolar configurations that create intricate patterns of field lines and particle trapping regions throughout the magnetosphere. The interaction between rogue planet magnetic fields and any retained atmospheric gas creates unique plasma physics environments that operate according to principles rarely encountered elsewhere in nature. Even trace atmospheres consisting of outgassed volatiles or sublimated surface materials can become ionized by cosmic ray interactions, creating tenuous plasma populations that are confined and organized by the planet's magnetic field into complex structures that extend far into space. Magnetic reconnection events in rogue planet magnetospheres, sudden changes in magnetic field configuration that release stored magnetic energy, occur on timescales and spatial scales very different from those observed around planets in stellar systems. Without the constant driving force of variable stellar winds, reconnection in rogue planet magnetospheres proceeds slowly and predictably, creating opportunities to study fundamental plasma physics processes in relatively undisturbed environments. The long-term evolution of rogue planet magnetic fields over billions of years reflects the gradual cooling and solidification of planetary cores as radioactive heat sources slowly decay. Young rogue planets with hot, vigorously convecting cores generate strong magnetic fields that gradually weaken as core temperatures decline and convection becomes less efficient. This evolutionary process creates a natural aging mechanism that could potentially be used to estimate the ages of individual rogue planets through magnetic field measurements. Binary rogue planet systems create particularly complex magnetic environments where the magnetic fields of two or more worlds interact across the empty space between them. These interactions can lead to magnetic field line connectivity between the planets, creating pathways for particle exchange and energy transfer that operate on timescales of years or decades as the planets orbit around their common center of mass. The magnetic shielding provided by rogue planet magnetospheres has important implications for the potential habitability of these worlds. Cosmic ray radiation, which poses significant biological hazards, is largely deflected by strong magnetic fields, creating protected zones where sensitive organic chemistry or even primitive life forms could potentially exist without suffering radiation damage. This magnetic protection extends not only to subsurface oceans, but also to any surface materials that might preserve organic compounds over geological timescales. Future spacecraft missions to nearby rogue planets would provide unprecedented opportunities to study magnetospheric physics in interstellar environments. Direct measurements of magnetic field strength, particle populations, and plasma wave activity could reveal fundamental aspects of planetary magnetism that are difficult to study in the complex environments around planets orbiting active stars. The detection of magnetic fields around rogue planets could also serve as a method for identifying these worlds through their radio emissions. Planetary magnetospheres generate radio waves through various plasma physics processes, and sensitive radio telescopes might be able to detect these emissions from nearby rogue planets, providing a new technique for discovering and characterizing these elusive objects. Comparative studies of magnetic environments around different types of rogue planets, rocky worlds, gas giants, and ice-rich planets, would reveal how planetary composition and structure affect magnetic field generation and evolution. These studies could help astronomers understand the relationship between planetary properties and magnetic activity across the full spectrum of world types found in the galaxy. The magnetic history preserved in rogue planet rocks and meteorites provides a record of how these magnetic environments have changed over cosmic time. Paleomagnetic studies of rogue planet materials could reveal periods of magnetic field reversals, strength variations, and other changes that reflect the thermal evolution of planetary interiors over billions of years of wandering through interstellar space. Atmospheric remnants and exotic weather. The atmospheric conditions on rogue planets represent some of the most extreme and unusual weather systems in the galaxy, where the absence of stellar heating creates meteorological processes that operate according to principles entirely different from those governing planetary atmospheres in stellar systems. These exotic atmospheric environments range from the virtually airless surfaces of small rocky rogue planets to the thick, slowly churning atmospheres of massive gas giant worlds that retain substantial gaseous envelopes despite their ejection into interstellar space. Smaller rogue planets, particularly those with masses comparable to Earth or Mars, lose most of their atmospheric inventory within millions of years after ejection from their parent stellar systems. Without the gravitational protection provided by a nearby star's magnetic field, and with surface temperatures dropping to near absolute zero, atmospheric gases either freeze onto the surface or escape into space through thermal and non-thermal processes. However, some atmospheric remnants may persist in unique configurations that create highly specialized weather patterns. The remnant atmospheres of rocky rogue planets consist primarily of gases with extremely low vapor pressures that can remain gaseous even at interstellar temperatures. Noble gases like argon and krypton, along with trace amounts of carbon dioxide and water vapor released by radioactive decay or outgassing from the planet's interior, create tenuous atmospheric envelopes that may persist for billions of years. These thin atmospheres experience weather patterns driven entirely by heat, conducted from the planet's interior rather than solar radiation. Convective processes in rogue planet atmospheres operate according to principles that reverse the normal relationship between surface and atmospheric temperatures. Instead of solar heating creating rising air masses from the surface, geothermal heat conducted through the crust creates localized warm spots that generate convection cells in the overlying atmosphere. These convection patterns can create persistent atmospheric circulation systems that remain stable for geological timescales. The absence of a day-night cycle on rogue planets eliminates the primary driver of atmospheric circulation on most worlds, creating opportunities for entirely different types of weather patterns to dominate. Global atmospheric circulation is driven instead by latitudinal temperature differences created by the planet's rotation and internal heat distribution, leading to wind patterns that can be remarkably stable and predictable compared to the chaotic weather systems found on planets with variable solar heating. Massive rogue planets, particularly gas giants that retain substantial hydrogen-helium atmospheres after ejection, exhibit atmospheric dynamics that operate in slow motion compared to the rapid weather changes seen on planets orbiting stars. Without intense stellar radiation to drive temperature differences, atmospheric circulation proceeds at a more leisurely pace, with storm systems that can persist for millions of years and wind patterns that change only gradually over cosmic timescales. The atmospheric composition of gas giant rogue planets preserves a record of the chemical conditions present in their birth environments, uncontaminated by ongoing atmospheric processing, driven by stellar radiation. These pristine atmospheric inventories provide insights into the composition of protoplanetary disks and the chemical processes that operated during the early phases of planetary system formation billions of years ago. Cloud formation processes on rogue planets involve condensation of atmospheric constituents at temperatures far below those encountered in stellar system environments. Exotic ices formed from methane, ammonia, carbon dioxide, and other volatile compounds create cloud systems with properties unlike anything found on planets warmed by stellar radiation. These clouds can persist in stable layers for geological periods, creating atmospheric structures that evolve only slowly over millions of years. The precipitation patterns on rogue planets involve the condensation and sublimation of atmospheric gases directly onto and from the planet's surface, creating weather phenomena that blur the distinction between atmospheric and surface processes. Snow and ice formation occur continuously in regions where atmospheric gases reach saturation, while sublimation from geothermally heated surface areas returns material to the atmosphere in endless cycles that can continue for billions of years. Atmospheric chemistry on rogue planets proceeds through reaction pathways that operate at extremely low temperatures and pressures, creating opportunities for the formation of complex organic molecules through processes that would be impossible in higher temperature environments. Cosmic ray bombardment provides the energy needed to drive chemical reactions in these cold atmospheres, potentially creating complex organic compounds that accumulate over geological timescales. The interaction between rogue planet atmospheres and magnetic fields creates unique magnetospheric processes where atmospheric constituents become ionized by cosmic ray interactions and are then organized by magnetic field lines into complex plasma structures. These processes can lead to atmospheric loss through magnetic field line reconnection events, but they can also create protective zones where atmospheric density is enhanced by magnetic confinement. Seasonal variations on rogue planets result not from orbital changes around a star, but from long-term evolutionary processes that affect atmospheric density, composition, and circulation patterns over millions of years. Changes in internal heat generation as radioactive elements decay can create slow atmospheric changes that represent the only form of seasonal variation these worlds experience. The study of rogue planet atmospheres provides unique opportunities to understand atmospheric physics under extreme conditions that serve as natural laboratories for testing theories of atmospheric dynamics, chemistry, and evolution. These environments represent end-member cases that help define the boundaries of what is possible for planetary atmospheric systems across the full range of conditions found in the galaxy. Atmospheric escape processes on rogue planets operate primarily through non-thermal mechanisms, such as sputtering by cosmic ray impacts and ionospheric outflow driven by magnetic field interactions. These processes proceed slowly but continuously over billions of years, gradually stripping away atmospheric mass and changing atmospheric composition in ways that reflect the planet's passage through different interstellar environments. The detection of atmospheric features on rogue planets presents significant observational challenges due to the extremely low temperatures and pressures involved. But future space-based infrared telescopes may be able to detect thermal emission from the warmest atmospheric layers of the most massive rogue planets. Such observations would provide direct information about atmospheric composition, temperature structure, and circulation patterns on these exotic worlds. Weather forecasting for rogue planets would involve predicting atmospheric changes that occur over timescales of thousands or millions of years, rather than days or weeks, as the slow evolution of internal heat sources and atmospheric escape processes gradually modify circulation patterns and chemical composition. These long-term atmospheric changes represent the only form of weather variability that rogue planets experience. The potential for atmospheric biosignatures on rogue planets depends on whether life forms in subsurface oceans could release detectable gases into the overlying atmosphere through geological processes such as volcanism or crustal outgassing. Even trace amounts of biologically produced gases could accumulate to detectable levels over the millions of years that characterize atmospheric evolution on these slowly changing worlds. The mechanics of planetary ejection. The violent events that transform ordinary planets into cosmic wanderers represent some of the most dramatic examples of gravitational dynamics in planetary systems, involving complex multi-body interactions that can accelerate worlds to velocities sufficient to escape stellar gravity entirely. These ejection processes reshape planetary system architecture while providing insights into the fundamental physical mechanisms that govern orbital evolution and stability over astronomical timescales. The most common pathway to planetary ejection begins during the early phases of planetary system evolution, when multiple massive planets interact gravitationally in ways that destabilize their orbits. Computer simulations reveal that planetary systems containing several giant planets often undergo periods of orbital instability that can last millions of years, during which planetary orbits become increasingly eccentric and unpredictable. These chaotic phases typically end when one or more planets acquire enough energy to escape the system entirely. The physics of gravitational ejection involves the transfer of orbital energy between planets through close encounters that act like gravitational slingshot maneuvers on a massive scale. When two planets approach each other closely, their mutual gravitational attraction deflects both objects from their original orbital paths, with one planet typically gaining orbital energy while the other loses energy. If the energy transfer is sufficiently large, the planet that gains energy can acquire enough velocity to exceed the escape velocity of the stellar system. Planet-planet scattering events that lead to ejection typically occur when orbital resonances between massive planets become unstable due to ongoing planetary migration or changes in the stellar system's gravitational environment. These resonances, which initially help stabilize planetary orbits by coordinating their orbital periods, can become sources of instability if perturbed by external forces such as gravitational interactions with passing stars, or the gradual loss of the protoplanetary disk that originally damped orbital oscillations. The velocity distribution of ejected planets reflects the gravitational binding energy of their original stellar systems and the efficiency of the energy transfer process during planet-planet encounters. Most ejected planets acquire velocities between 10 and 50 miles per second relative to their parent stars, though some extreme ejection events can accelerate planets to much higher velocities that carry them completely out of their birth galactic regions. Multi-planet ejection events can occur when gravitational instabilities affect several planets simultaneously, creating cascades of ejection that can remove most of the original planetary population from a stellar system over relatively short timescales. These dramatic reorganization events help explain why many observed exoplanetary systems contain fewer giant planets than theoretical models of planetary formation would predict, with the missing planets having been ejected during early phases of system evolution. The timing of planetary ejection events appears to be concentrated during the first few 100 million years after planetary formation, when systems still retain enough dynamical energy to drive large-scale orbital changes. However, ejection can continue at lower rates throughout the lifetime of planetary systems, particularly in environments where external gravitational perturbations from passing stars or galactic tidal forces can trigger delayed instabilities in otherwise stable orbital configurations. Binary star systems present special challenges for planetary orbital stability, with the gravitational influence of two stellar masses creating complex dynamical environments where planetary ejection can occur through different mechanisms than those operating in single-star systems. Planets in binary systems may be ejected when their orbits become unstable due to the changing gravitational field created by the orbital motion of the two stars, or when close encounters between the stars themselves disrupt planetary orbits through tidal interactions. The ejection process can preserve some orbital relationships between planets if multiple worlds are ejected simultaneously or in rapid succession. Binary rogue planet systems represent cases where two planets manage to retain their gravitational bond despite being ejected from their parent system, creating miniature planetary systems that orbit around their common center of mass while traveling through interstellar space together. The direction and velocity of planetary ejection depend on the specific geometry of the gravitational encounter that triggered the ejection event, creating rogue planet populations with diverse kinematic properties that reflect the wide range of possible ejection scenarios. Some rogue planets travel through the galaxy at high velocities that indicate violent ejection events, while others move more slowly, suggesting gentler ejection processes or subsequent gravitational interactions that modified their trajectories. Planetary migration processes that bring giant planets closer to their parent stars can create conditions that favor ejection by increasing the likelihood of close gravitational encounters between massive worlds. The inward migration of giant planets through protoplanetary disks often results in orbital configurations that become unstable once the disk material is depleted and can no longer damp orbital oscillations through gravitational drag. The mass ratio between interacting planets strongly influences ejection outcomes, with encounters between planets of similar mass, typically resulting in one planet being ejected while the other remains bound to the star on a modified orbit. Encounters between planets of very different masses tend to produce smaller orbital changes, though repeated encounters can eventually accumulate enough energy transfer to trigger ejection of the smaller planet. Stellar flyby events represent another mechanism for planetary ejection, particularly in dense stellar environments such as young star clusters, where close encounters between stellar systems occur frequently. When a passing star approaches within a few hundred astronomical units of a planetary system, its gravitational influence can perturb planetary orbits sufficiently to trigger ejection, especially for planets in the outer regions of the affected system. The angular momentum conservation during ejection events determines the final orbital characteristics of both ejected and remaining planets, with the total angular momentum of the system being redistributed among all participating objects. This redistribution can lead to significant changes in the orbital eccentricity and inclination of remaining planets, creating planetary systems with unusual architectures that preserve evidence of past ejection events. Tidal interactions during close planetary encounters can cause additional complications in the ejection process, particularly for planets with significant atmospheric envelopes or satellite systems. Strong tidal forces can strip away atmospheric material or disrupt satellite orbits, potentially leaving ejected planets with modified physical properties compared to their original configurations before ejection. The statistical analysis of rogue planet populations provides insights into the frequency and efficiency of ejection processes throughout galactic history, revealing how common these dynamical instabilities have been in planetary systems and how they have influenced the overall distribution of planetary mass between bound and free-floating populations. Understanding ejection mechanisms helps astronomers predict which types of stellar systems are most likely to produce rogue planets and under what circumstances ejection events are most probable. Now, close your eyes and picture how all of this might look. Imagine a young planetary system 4 billion years ago with several massive worlds slowly orbiting through the remaining debris of planetary formation. Watch as their gravitational dance becomes increasingly chaotic over millions of years, with orbital paths that swing closer and closer together until one fateful encounter sends a world accelerating outward, past the outer reaches of its birth system, beyond the gravitational embrace of its parent star, and into the vast darkness where it will wander alone for the rest of cosmic time. Future exploration and discovery. The next decades promise revolutionary advances in our ability to detect, characterize, and potentially visit rogue planets, as new technologies and observational strategies open unprecedented windows into these hidden populations that may dominate the galaxy's planetary census. These advances will transform rogue planets from theoretical curiosities into tangible targets for scientific investigation and possibly even direct exploration by robotic missions launched from Earth. The Nancy Grace Roman Space Telescope represents only the beginning of a new generation of space-based observatories, specifically designed to find and study free-floating planets across a wide range of masses and distances. Future missions building on Roman's pioneering microlensing surveys will push sensitivity limits to detect rogue planets as small as Mercury, or even smaller rocky worlds, providing the first complete inventory of planetary mass objects drifting through interstellar space in our galactic neighborhood. Advanced infrared telescopes currently in development will complement microlensing surveys by directly detecting thermal emission from the warmest rogue planets, particularly young gas giants that still retain substantial heat from their formation processes. The James Webb Space Telescope and its successors possess the infrared sensitivity needed to observe the faint thermal glow of massive rogue planets located within a few hundred light-years of Earth, providing direct measurements of their atmospheric compositions and temperature structures. Ground-based telescope networks are being expanded and upgraded specifically to support rogue planet discovery efforts through improved microlensing capabilities and enhanced follow-up observations of candidate events. These networks will work in coordination with space-based missions to provide comprehensive coverage of the sky and enable rapid response to transient microlensing events that might reveal the presence of Earth mass or smaller rogue planets. Machine learning algorithms are revolutionizing the analysis of astronomical data from rogue planet surveys, enabling the automated identification of subtle microlensing signatures that might be overlooked by traditional analysis methods. These artificial intelligence systems can process the enormous datasets generated by wide-field surveys to identify candidate rogue planet events with unprecedented efficiency and accuracy, dramatically increasing the discovery rate of these elusive objects. The development of gravitational wave detectors with enhanced sensitivity to low-frequency signals may eventually enable the detection of rogue planets through their gravitational effects on space-time itself. While current gravitational wave observatories are optimized for detecting merging black holes and neutron stars, future space-based detectors might be sensitive enough to observe the gravitational signatures of rogue planets passing through our solar system. Direct exploration missions to nearby rogue planets represent one of the most ambitious goals in planetary science, requiring revolutionary advances in propulsion technology and autonomous spacecraft systems. The closest rogue planets to Earth may be located within 10 to 20 light-years of our solar system, making them potentially accessible to interstellar probes powered by breakthrough propulsion concepts such as fusion rockets, antimatter engines, or light sails accelerated by powerful laser arrays. Robotic missions to rogue planets would face unprecedented challenges in navigation, communication, and operation in the extreme environments of interstellar space. These spacecraft would need to operate autonomously for decades or centuries while traveling through the emptiness between stars, requiring advances in artificial intelligence, radiation shielding, and power systems that can function reliably over interstellar distances and timescales. The scientific objectives of rogue planet exploration missions would include detailed characterization of surface and atmospheric conditions, searches for subsurface oceans and potential biosignatures, and investigations of internal structure through seismic monitoring and magnetic field measurements. These studies would provide ground truth for theoretical models of rogue planet evolution and habitability, while potentially discovering entirely new forms of planetary environments. Sample return missions from rogue planets could provide the ultimate scientific prize by bringing materials from these exotic worlds back to Earth for detailed laboratory analysis. Such missions would require even more advanced propulsion and spacecraft technologies, but could yield revolutionary insights into planetary formation processes, the potential for life in extreme environments, and the history of early planetary system evolution. Communication with interstellar missions to rogue planets would require new approaches to deep space communications that can maintain contact across distances measured in light years rather than astronomical units. Advanced laser communication systems and large-scale radio telescope arrays on Earth would be needed to receive scientific data from spacecraft exploring rogue planets in neighboring stellar systems. The search for atmospheric biosignatures on rogue planets will benefit from advances in spectroscopic techniques that can detect trace gases produced by potential subsurface life forms. Even extremely low concentrations of biologically produced compounds could accumulate to detectable levels in the thin atmospheres of rogue planets over geological timescales, providing potential targets for biosignature detection by future space telescopes. Citizen science projects involving amateur astronomers and volunteer data analysts are expected to play important roles in rogue planet discovery efforts, particularly in the analysis of microlensing light curves and the identification of unusual infrared sources that might represent nearby rogue planets. These collaborative efforts can supplement professional astronomical surveys by providing additional data processing capabilities and fresh perspectives on unusual observations. International cooperation in rogue planet research will be essential for coordinating the complex observational campaigns needed to detect and characterize these objects across multiple wavelengths and observation techniques. Joint missions between space agencies and shared telescope time allocations will maximize the scientific return from limited observational resources while fostering global collaboration in this frontier area of astronomy. The economic implications of rogue planet discoveries may eventually extend beyond pure scientific interest if these worlds prove to contain valuable resources or serve as waypoints for interstellar exploration. Rogue planets rich in water ice, rare metals, or other materials could become targets for future space mining operations, while strategically located rogue planets might serve as refueling stations or research bases for missions traveling between stellar systems. Educational outreach programs focused on rogue planet science provide unique opportunities to engage public interest in astronomy and planetary science through the compelling story of worlds wandering alone through cosmic space. These programs can inspire new generations of scientists and engineers while building public support for the ambitious missions and technologies needed to explore these distant worlds. The technological spin-offs from rogue planet research are expected to benefit many other areas of space science and exploration, particularly in the development of sensitive detectors, advanced propulsion systems, and autonomous spacecraft technologies. The extreme requirements of rogue planet missions will drive innovations that can be applied to lunar and planetary exploration, asteroid mining, and other space applications that require operation in challenging environments. Long-term planning for rogue planet exploration involves coordinating research efforts across multiple decades to build the scientific foundation and technological capabilities needed for ambitious interstellar missions. This long-term perspective requires sustained commitment from funding agencies, international partnerships, and the scientific community to maintain progress toward the ultimate goal of directly exploring these mysterious, wandering worlds.